Okay, students, welcome again. Now we'll talk about chapter 12. We have three selected topics. The first one is the gravity law, and we have the Kepler's laws, and the description of tides. Okay, we need just to deal with this law, which is the Newton's gravitational law. Okay, we don't need to solve anything else in this chapter, just we need to look at this one. Okay, Newton's have three laws in mechanics, in motion: first and second and third. This is the fourth one, which is the gravitational law. Newton's law know that, and all of us are know also that if we have two bodies, first with mass m1 and the second with mass m2, and the distance between them is r, then there is a attractive gravitational force between them. This force depends on the mass and reversibly with r. Okay, r from m1 to m2 and from m2 to m1. And this case, the force depends on the masses, the multiplication of the masses, and reversibly with the r squared. The constant to change the relation from the relation to equality, we need to use this constant, which is the gravitational universal constant, which is 6.67 multiplied by 10 to minus 11. Okay, and its unit is Newton meter squared over kilogram squared. And this force is always attractive. Okay, let us look at this example. What if there is a person with mass m standing on the earth with mass m, earth, me? The radius of earth is re. The mass of the man is 70 kilograms. The mass of the earth is almost approximately 6 multiplied by 10 to 24 kilograms. The radius of the earth approximately is 6.37 multiplied by 10 to 6 meters. Okay, now we know that the formula of this, the attractive force, gravitational force, is F is equal to G multiplied by M for the man, multiplied by M for the earth, and divided over the radius between the center. From here, we need the radius between the center of these masses. Always we take these masses as a point mass. Okay, the radius between the center of the earth and the center of the man is r small, which is equal to r capital, which is the radius of the earth if we assume it as a uniform sphere, plus approximately 1 meter, the altitude of the center of mass of the man. But if the earth radius is 6 million meters, then we can cancel this meter, and we can assume that the distance r small between the two bodies, which is the man and the earth, is the earth's radius re. Okay, now we can assume that r is the distance, is re. In this case, the force will be G m for the man, m for the earth, divided by the radius of the earth, because the man at altitude 0 from the earth. Okay, putting the numbers, then we can find that the force between the man and the earth, which is attractive force to the center of the earth and to the center of the man, because of the third in Newton's law, which is tell us there is action and reaction between the man and the earth. the force is 690.7 newtons. Okay, what if we need to compute the weight of the man? The weight, as we know, it is the force between the man and the earth. It is the same force. So using the second Newton law, which is ma, and a is g at surface, which is approximately 9.8, then the weight of that man is 686 newtons, which is almost the same as the force between the man and the earth. Look, we don't have this, we have just, the difference is just less than 4 newtons, but this is an average value. Okay, look, now if we need to compute the acceleration, if we have a force, then we have acceleration. Okay, using Newton's second law, we know that the Newton's second law, F is equal ma. Then the acceleration on the man, for the man, is the force divided by the mass of the man, which is equal to 690.6, which is the force, divided over the mass of the man, which is 70. This will give us the acceleration is equal to 9.8671 and etc. meters per squared second, which is the same g. This g is approximated value of this one. So the acceleration for anybody on the surface of the earth is g is 9.8. Okay, what is the acceleration for the earth? It is the same. We need to use the force, which is F, divided over the mass of the earth. It is not the mass of the man. It is a huge quantity, which is 6 multiplied by 10 to 24. Okay, this will give us 1.15 multiplied by 10 to minus 22 meters per square second. It is almost zero. It is not zero, it is almost zero. Okay, in this case we can see that there is acceleration on the man and there is acceleration on the earth, but the acceleration on the earth is neglected. It is near zero because the mass of the earth is huge. And we can, if you need to understand that the man is going toward the center of the earth and the earth is going with this acceleration to the center of the man. But the time, not just the man, for anybody, but the time when this body, the man's body or the pin body mass going to the center of the earth, it is reaches the surface of the earth immediately, and the earth will not move any distance because of any object on it. Okay, now by the same way, please try to solve these examples. I need you to look at this first one. We have two persons, the first one with mass 60 kilograms and the second is with mass 70 kilograms, and the distance between them is 5 meters. Okay, we have two masses and the distance between them, and we have g, which is constant, 6.6 e minus 11. Okay, also, what if we have a satellite and space shuttle? The distance between them is 1,000 meters. The mass of the satellite is 30 tons and the mass of the space shuttle is 400 tons. Compute the force between them and the acceleration. I will tell you. What if we have the earth? We know its mass, and we have a far star. Let us call it Alpha Centauri, for example, which is far away, which is the nearest star to us after the sun, which is about 4 light years, and its mass, for example, 4 multiplied by 10 to 32 kilograms. It is heavier than the earth, and the distance is 4 light years. To convert that, 1 light year is equal to 9.5 multiplied by 10 to 15 meters, and you see that in the labs workout, and you can convert the light year to meters. Okay, you have the mass and the distance. You have the g, the constant, and find the force between them, for between each body, the gravitational force, and then find the acceleration for each object. Yes. Okay, it's easy. Directly you can apply the formula and find the answers. Thank you.